Welcome everyone to a deep dive into one of the most transformative technologies in modern AI, the transformer architecture. Our topic today is the expanding vision of transformers, from pixels to dialogue. We are charting the incredible journey of how this architecture, initially designed solely for processing text and language, has evolved to handle virtually every form of data imaginable. If you look at the visualization here, you can see the core concept we'll explore. We start on the left with disparate forms of input, sequences of letters representing text and blocks of pixels representing images, or perhaps even sequential DNA data shown by the scattered letters. These inputs are converted into a unified grid format, a sequence of tokens that the transformer can process. Crucially, once processed, the model isn't restricted to generating text alone. It can output structured data like text sequences for dialogue, visual representations like images, or even sequential data like audio waveforms. This ability to convert any input modality into any output modality, essentially building a universal interface for AI, is the expansive vision we aim to detail today. When the transformer architecture was first introduced, its success was immediate and undeniable in the domain of natural language processing. Models like BERT and GPT quickly mastered language because text naturally aligns with the transformer's core strength, processing discrete, ordered sequences of tokens. But the next great challenge, the next frontier, was vision. Images present a significant difficulty. They are inherently continuous, spatial, and lack that obvious sequential structure that text provides. Think about it. A sentence is a clear sequence of words, but where does an image begin and end its sequence? The traditional approaches used in vision, like convolutional neural networks, or CNNs, were built explicitly with spatial biases that transformers lacked. This presentation is organized into two major acts detailing how this challenge was overcome. Act 1 focuses on the architectural breakthroughs necessary to teach transformers to see, to effectively become strong vision models, overcoming their initial limitations. Act 2 then tackles the synthesis of vision and language, showing how we created a common language for multimodal AI, allowing models to reason about what they see. Before the pure vision transformer emerged, the concept of attention was already starting to bridge the gap between vision and sequence models. Our journey begins with the concept of RNNs utilizing visual attention. In early image captioning models, a convolutional neural network, or CNN, would extract the base image features. Then, a recurrent neural network, or RNN, would generate the caption word by word. The critical innovation was the attention mechanism, which allowed the RNN to focus, or look, at specific parts of the image feature map corresponding to the word it was currently generating. For example, when generating the word frisbee, the model would attend primarily to the flying object in the image. The key insight here was explainability. Attention showed us what the model cared about when generating a specific output. This idea led directly to the CNN transformer hybrid architecture, notably the detection transformer, or DETR. DETR used a CNN backbone to generate feature maps, which were then converted into a sequence of tokens and fed into a standard transformer encoder-decoder setup to predict object bounding boxes. This was a huge step forward for object detection, but it had a key limitation. The CNN was still doing the heavy lifting of visual perception, managing all the spatial understanding. The fundamental question remained: if the transformer is so powerful, can we get rid of the CNN entirely? The answer to eliminating the CNN came with a resounding yes, in the form of the vision transformer, or ViT. This breakthrough proved that a pure transformer could master vision, provided we adapted the input format. The conceptual leap was encapsulated in the phrase, "An image is worth 16 x 16 words." The process is structured into 3 simple steps. Step 1 is patching. We chop the high-resolution input image into a rigid grid of fixed-size patches, typically 16 by 16 pixels. This turns the continuous image into a collection of discrete blocks. Step 2 is flatten and project. Each spatial patch is flattened into a single vector. This vector is then linearly projected into a higher dimensional embedding space, essentially turning it into a visual token equivalent to a word token in NLP. Step 3 is process like text. We add positional embeddings to maintain some spatial awareness and include a special classification token, the CLS token, just like in BERT. The entire sequence of patch tokens is then fed into a standard transformer encoder. ViT, trained at scale, achieved state-of-the-art results in image classification, fundamentally changing the vision landscape. However, this performance came at a cost, known as the catch. Transformers inherently lack the inductive biases that CNNs possess, such as translation invariance and locality. To overcome this architectural disadvantage, the original ViT was incredibly data-hungry, requiring training on over 300 million images to outperform its CNN counterparts. The major hurdle for widespread ViT adoption was the extreme data requirement. Researchers quickly developed two elegant solutions to solve this data problem, allowing ViTS to be trained competitively without requiring billions of proprietary images. The first solution is DETR, the data-efficient image transformer, which leverages knowledge distillation. The concept is straightforward. Use a powerful, pre-trained CNN as a teacher model. The ViT, or student, is then trained on two signals. First, the traditional hard targets, which are the true image labels, and second, the soft targets, which are the probability distributions produced by the teacher CNN. The student learns not just the final answer, but the nuances and confidence levels the expert teacher exhibits. A special distillation token is added to the input sequence specifically to learn the teacher's output. DETR proved that we could achieve competitive results on ImageNet without any extra training data beyond the standard set. The second, more radical solution is Dino, which uses self-supervision. Dino learns visual representations entirely without labels, utilizing a technique called self-distillation. It trains a student network to match the output of a teacher network. Crucially, the teacher network's weights are an exponential moving average, or EMA, of the student's own weights, which keeps the teacher stable and slightly lagging. The networks see different augmented views of the same image. For example, one sees a cropped view while the other sees the global view. Dino demonstrated a deep, unsupervised understanding of image structure, learning implicitly to segment objects from backgrounds without ever being explicitly taught to do so, solely by training the student to match the teacher's stable output. Once classification was mastered, the next set of challenges for vision transformers lay in dense prediction tasks. The standard ViT architecture processes the entire image at a single, fixed patch scale, outputting a single set of feature embeddings. While this works well for classifying the whole image, it makes it ill-suited for tasks that require detailed, pixel-level understanding at multiple resolutions. Consider two specific dense prediction tasks. First, semantic segmentation, which requires assigning a class label to every single pixel in the image. Second, object detection, which requires precisely locating and bounding objects of various sizes, from a small bird to a large truck. These tasks thrived on CNN architectures that built feature pyramids, generating hierarchical feature maps that capture detail at high resolution and context at low resolution. The standard ViT simply couldn't compete here. Therefore, the architectural question became, how can we adapt the transformer to produce these necessary multi-scale feature maps, mimicking the powerful feature pyramids that made CNNs so effective for these fine-grained tasks? To address the resolution challenge, researchers introduced two major hierarchical architectures, moving away from the flat structure of the original ViT. Architecture 1 is the Pyramid Vision Transformer, or PVT. PVT creates a feature pyramid similar to CNNs by processing the image in multiple stages. At each stage, the patch embeddings are merged together, which simultaneously decreases the spatial resolution and increases the channel depth. This naturally creates the multi-scale representation required for detection and segmentation. However, standard self-attention scales quadratically with input size, making high-resolution feature maps prohibitively expensive. To manage this computational cost, PVT introduced spatial reduction attention, or SRA. SRA drastically downsamples the keys and values before the attention calculation, dramatically reducing the computational complexity while retaining the necessary information. Architecture 2, and arguably the most impactful, is the SWIN transformer. The SWIN transformer achieves linear complexity with respect to image size, making it highly scalable, which is essential for high-resolution images. It achieves this efficiency by calculating attention only within local, non-overlapping windows, a mechanism called windowed multi-head self-attention, or WMSA. To ensure that information can still flow between these separate windows, the SWIN transformer utilizes a crucial trick. In alternating layers, it shifts the window configuration, creating the shifted window multi-head self-attention, or SWMSA. This shifting mechanism allows for cross-window communication, ensuring information propagates efficiently across the entire image. The breakthroughs delivered by the vision transformer, the data efficiency techniques of DETR, and the hierarchical scalability of the SWIN transformer collectively led to what we might call a Cambrian explosion in the field. Vision transformers were now established as powerful, general-purpose perception backbones. The architectural focus shifted to optimizing training and application. We saw specialized techniques emerge. One major branch focused on masked image modeling, or MIM, which includes models like BERT and MAE. These techniques adapt the fill-in-the-blank, pre-training task from NLP by masking image patches and predicting their content. Another branch explored weight averaging, which led to concepts like modal soups, showing how combining the weights of multiple fine-tuned models can lead to superior performance. And finally, a third branch focused on massive, state-of-the-art foundation models like EVA and IJEPA, pushing the limits of what large-scale pre-training can achieve. With transformers now fully capable of seeing with high fidelity and efficiency, the focus shifted to a more profound challenge: the next frontier. This involves moving beyond mere perception to enabling models to truly understand and reason about what they see by connecting the acquired visual knowledge to the established domain of language. Act 2 begins with the task of creating a common language, a framework where vision meets text. The overall goal is to move far beyond simple perception and build models that can handle heterogeneous data types, such as images and text, simultaneously, and critically, capture the complex interactions and meaning between them. This process boils down to two major challenges: fusion and alignment. Fusion asks, how do you combine information from fundamentally different modalities, such as sequences of pixels and sequences of words, into a single, shared representation space? This is about mixing the data streams. Alignment asks, how do you discover the semantic relationships between elements in these different modalities? For example, how does the model learn that the token, cat, corresponds precisely to the visual features of the feline object in the image? The visualization demonstrates these streams of data, visual tokens and text tokens, flowing into a central processing unit, the fusion and alignment engine. The key tool that makes both fusion and alignment possible is the transformer's attention mechanism. Attention is uniquely powerful, acting as a dynamic cross-reference tool for both fusion, by combining different token embeddings, and alignment, by finding structured patterns within and across those different modalities. Early multimodal models explored two primary architectural strategies for combining vision and language. Approach 1 was the single-stream architecture, exemplified by models like BERT. In this design, text tokens and visual tokens are pre-processed and then simply concatenated together. This single, long sequence is then fed into a standard, unified transformer encoder. The model processes the data as one large chunk of sequential information. While simple, the limitation of this approach is that it treats all modalities identically from the start, even though text and visual data typically require fundamentally different levels or types of processing. Approach 2 countered this by introducing the dual-stream architecture, a prime example of which is BERT. This approach recognizes the unique needs of each modality. Each data type, whether text or vision, is first processed in its own dedicated specialized transformer stream to develop high-level unimodal representations. For example, a text transformer handles the language tokens, and a vision transformer handles the visual tokens. The key innovation here is co-attention, which acts as the bridge. The two streams exchange information through a bidirectional cross-attention mechanism. The query from one stream attends to the keys and values of the other stream, allowing targeted information exchange. The major advantage of the dual-stream approach is that it allows the model to develop a robust, individual understanding of each modality before reasoning about their complex interactions, generally leading to more precise alignment. A monumental breakthrough in alignment came with the introduction of CLIP, which utilized contrastive learning. This approach represented a major paradigm shift. Instead of trying to intricately fuse the modalities inside a single complex model, CLIP trains two completely separate encoders, one for images and one for text, to perform a simple yet powerful task. The goal is to map matching image-text pairs to similar vectors in a shared, high-dimensional embedding space, while simultaneously pushing non-matching pairs far apart. The diagram illustrates this clearly. Matching pairs, shown along the diagonal, are trained to be pulled together using cosine similarity. Mismatched pairs, which are every other box off the diagonal, are pushed apart. This massive contrastive training process, conducted on hundreds of millions of image-text pairs scraped from the internet, forced the model to learn deep, abstract semantic concepts connecting vision and language. The power of CLIP results in a remarkable emergent capability: zero-shot classification. Because CLIP has learned the underlying semantic relationship between images and text, it can classify images without needing explicit training on those classes. To classify a picture of a dog, you simply provide text descriptions like a photo of a dog, a photo of a cat, and so on. The model identifies which text vector is most similar to the image vector, effectively classifying the image based on language understanding alone, instantly expanding the model's utility. The mastery of multimodal alignment paved the way for the most exciting public-facing application: text-to-image generation, or the generative leap. We can trace this through the evolution of DALL-E. Model 1 was the original DALL-E. Its architecture was a single, large GPT-style decoder model. The mechanism was purely sequential and autoregressive. It was trained to predict the next token in a combined sequence starting with the text tokens, followed immediately by the visual tokens. These visual tokens were discrete codes generated by a discrete variational autoencoder, or DVAE, which compressed the visual information. The inference process was straightforward. Given a text prompt, the model generated the sequence of visual tokens, which the DVAE then decoded back into an image. This was groundbreaking but often produced less coherent results. Model 2, DALL-E2, introduced a much more modular, two-stage system, fundamentally improving quality. The mechanism relies heavily on the power of CLIP. In Stage 1, the text prompt is fed into a frozen CLIP text encoder to generate a high-quality semantic text embedding. This embedding captures the meaning of the prompt. In Stage 2, a diffusion model uses this rich text embedding as a direct guide to generate a new image that aligns semantically with the prompt. The impact was profound. DALL-E2 produced significantly higher quality and far more coherent images than its predecessor, demonstrating the immense power of leveraging CLIP's semantic space for robust, creative generation. As models grew and inputs became higher resolution, we hit a fundamental computational wall with the standard transformer: quadratic scaling. Standard transformers cannot handle massive raw inputs, like individual pixels, because the sequence length would be enormous, making self-attention computationally intractable. The universal interface, realized in architectures like the perceiver, solves this problem using what is called a latent bottleneck. Instead of processing the massive raw input array directly, the perceiver introduces a small, fixed-size set of latent tokens as its primary working memory. The first key step is that the massive raw input array, which could be 50,000 pixels or more, is only ever accessed via a specialized mechanism called cross-attention. The latent tokens act as queries that attend to the raw input, extracting only the relevant information needed for the task, effectively summarizing the input. The second key step is that the core processing and iterative refinement then happen entirely within the compact latent array using standard self-attention. Since the size of the latent array is fixed and small, this self-attention processing is extremely cheap, scaling linearly with the input size rather than quadratically. This clever design makes the perceiver a truly modality-agnostic architecture. It can seamlessly process images, audio, video, or even point clouds with the exact same core model, simply by changing the raw input size while keeping the internal computational cost manageable. The culmination of this research journey is the grand synthesis, the realization that we do not need to train a monolithic, multimodal model from scratch. Instead, we can leverage massive, billion-parameter foundation models that are already experts in their respective domains, such as vision or language, and keep them frozen. The challenge then simplifies to efficiently bridging these two giant models. We examine two leading examples of this bridging strategy. Example 1 is Flamingo. Flamingo connects a frozen vision encoder with a frozen large language model. The bridge component is twofold. First, it uses a perceiver resampler, taking inspiration from the perceiver architecture, to condense the vast vision features into a small, fixed number of latent tokens. These condensed tokens are then fed to the LLM via newly inserted, trainable gated cross-attention layers. Only these small gated attention layers are trained, allowing the LLM to process visual information without corrupting its language expertise. Example 2 is BLIP2, which utilizes an innovative component called the Q-former. The Q-former is a lightweight transformer designed specifically to extract the most relevant, compressed visual features needed for the language task. A simple linear layer then maps these Q-former features directly into the frozen LLM's input space. This effectively teaches the LLM to interpret the Q-former's visual summaries. Both Flamingo and BLIP2 demonstrate the power of this paradigm. They create exceptionally powerful few-shot vision language models, or VLMs, capable of performing a vast range of tasks like visual question answering, captioning, and visual dialogue, often without requiring any extensive fine-tuning on specific tasks. We have witnessed how the journey from raw pixels to coherent dialogue has laid the fundamental groundwork for AI that perceives, understands, and interacts with the world in increasingly holistic ways. The field is now rapidly expanding beyond the initial image and text, pairing into a truly multimodal ecosystem, as depicted by the central hub connecting all these different data types. We are seeing incredible open-source excellence, with models like LLaVIA pushing the boundaries of open vision language chat capabilities. Furthermore, the expansion is moving beyond just vision. Models like ImageBind learn a joint embedding space across 6 different modalities, including thermal images and depth information, and Seamless M4T provides unified translation across speech and text, demonstrating the integration of audio. Perhaps the most exciting frontier is embodied AI. Models such as PyLM-E and RT2 connect vision language understanding directly to robotic control, allowing the models to generate physical actions in the real world instead of just generating text responses. Finally, the commercial state-of-the-art, demonstrated by models like GPT-4, Gemini, and Sora, showcases the immense capabilities of large-scale multimodal systems in production, proving that these sophisticated architectures can handle complex, real-world tasks. The vision of the transformer has indeed expanded, transforming AI into a truly universal intelligence platform. Thank you.